I wanted to finish the overview stuff. I put quite a bit of material on the net, if you can see it. Has anybody seen it? I think I'll just tune it in rather than write it out again. So I wrote this up just to give you another handle on some of the definitions and stuff. And this is essentially an overview of everything, and plus a little bit more that is in Chapter 1. So there's a couple of basic ideas before you can even talk about what an integral is. And here's the theme in all of these integral constructions. First of all, we're building definite integrals, right? We're building things that ordinarily are real numbers. And they all have the cachet that they're areas under curves calculated by dividing the area under a curve up into miniature rectangles and somehow letting the process become accurate by letting the rectangles get infinitesimally small and adding them up somehow along the way. That's the theme that runs throughout the construction of definite integrals. You can have a definite integral and not have the notion of a fundamental theorem of calculus. A fundamental theorem, I say a fundamental theorem of calculus because for every integral there will be one. A fundamental theorem of calculus is a theorem which allows you to evaluate one of these definite integrals by the process of finding an antiderivative and evaluating it at two places and taking the difference, as we are taught to do at the very beginning when we learn calculus the first time. So the fundamental theorem of calculus is the one that connects the integrand as the derivative of the function, the antiderivative, right? It connects derivative and antiderivative. You can talk about an integral, a definite integral, in the absence of that. The fundamental theorem of calculus, if you will, is an evaluative theorem. The integral itself is a construction where the attempt is made to be as general as possible. In other words, any integral or any function whose graph we can draw and get the area or have some concept of what the area is under the graph, we would like that process to be as general as possible. And that's what has driven hundreds of years' worth of integral making. We saw that in the 1630s, Fermat was able to integrate the power curves, and I'll revisit that today the way it's usually done in the calculus book. And if you haven't seen it recently or at all, where we're actually going to sum up the rectangles and let them get arbitrarily small and get an integration. The first integral, definite integral that was defined was Cauchy's integral in 1823. And then Riemann in 1854, more or less as an afterthought, in the course of a paper he was writing on trigonometric series. And then about 1875, a Frenchman by the name of Gaston Darboux, D-A-R-B-O-U-X, you see it here in a second, decided he thought Riemann's definition could be improved upon, made simpler, and he invented the Darboux integral, which is equivalent to the Riemann integral. Two integrals are equivalent if they integrate the same classes of functions, right? Things rocked along like that until in the late 19th century. Some embarrassing functions came up that caused people to say, can we generalize the integral that we have now and integrate yet more stuff? And the Lebesgue integral was capable of doing it. Henri Lebesgue invented that in 1902. Published, in fact, as part of his doctoral dissertation in 1902. And people, a lot of names that would be familiar to you, Morel, Jourdain, organic terms theorem and all that. These guys were all working on the concept of measure, the generalization of length, area, and volume, which was to be incorporated in these new definitions of integral. So Lebesgue invented the Lebesgue measure and the Lebesgue integral, which was a radically different approach from anything that had been done before. I'll explain why. And then things rocked along a little bit longer, and in the mid-50s, mid to late 50s, a couple of guys came up with yet an improvement on the Lebesgue integral, but harken back to the original Riemann definition. So we went the Lebesgue route, which was radically different, and we sort of went back to the Riemann definition with a couple bells and whistles on it that made it even more powerful than the Lebesgue integral. And that's called the Henstock-Kurzweil integral. There's a lot of different people that research these things, so the names aren't totally consistent. Sometimes you'll call it, or you'll see that the Henstock-Kurzweil integral is also called the McShaney integral. And in the teens, a whole lot of work was done. Lebesgue sort of opened the floodgates. In the early teens, a fellow by the name of Perron, P-E-R-R-O-N, came up with an alternative formulation of the integral, but ultimately was equivalent to the Henstock integral, but it's not obvious from what he did way back when. Another fellow by the name of Denjoy, about the same period of time, 1914 or so, came up with yet another definition. In 1918, an Englishman by the name of Daniell, D-A-N-I-E-L-L, P.J. Daniell, I guess improved is the word, presented his integral, the Daniell integral, which is equivalent to the Lebesgue integral, and it represents a vast simplification in the definition so that it's easier to work with. One of the things that you would like in a decent integration theory is to have definitions that are easy to use. You've probably noticed this in analysis. If you appeal to the original definition of derivative, it's a limit of the difference quotient. That's the 1821 Cauchy definition. You know, the limit is h goes to 0 of the quantity, a fraction, x plus h minus f(x) over h. Remember, we do that for zillions of functions. Taking limits like that is a pain in the ass. And Weierstrass offered an improvement in the early 1860s where the derivative was couched totally in terms of continuity, which is easier to check. And then a Greek-German mathematician by the name of Constantine Kara-Theodori, as recently as 1950, improved on that. So there's the Kara-Theodori definition of derivative, which is also based on continuity, but it's even simpler than the Weierstrass one. It's one of those things that if you sit down and try to prove the chain rule of calculus from scratch, totally rigorously, you will have a problem if you use the original Cauchy definition. The equivalent Kara-Theodori definition makes it not trivial, but makes it much, much easier. So that's a goal in the back of everyone's mind. Frame the definitions so that things are easier to prove. Okay? So, with that in mind, a few definitions. What's a partition? We partition closed intervals. Integrals are done over closed intervals. And a partition is a set of points that at least has the endpoints of the interval in it and other points in between, generally. And you can write them down in order from the least to the greatest, right? And see what you got. Every time you have two successive points in that order, you define a subinterval, and you chop up the domain of integration. You have a bunch of little subintervals. Do they overlap or not? Are there any common points between adjacent subintervals? Why, yes, there are. Namely, the partition points are common. It's the high end of the lower one and the low end of the higher one, right? As you go along. Okay. Keep that in mind. In the Riemann setting, that's what you do. You have the subintervals are closed at both ends. In the Lebesgue formulation, They're open at the high end, closed at the low end. Just a quirk of the if you want to refer to a partition sort of generically, it's the set of points. Is it finite or infinite? Do you have an infinite partition? Well, you can have an infinite partition, but is that a legitimate thing in integration theory?